continue today talking about matrices and their particular properties. I kind of finished the last section. I just missed a point. Well, I didn't really miss a point. I chose to ignore it. Huge difference. But there's a particular theorem which I wish to discuss because it's written in this fancy verbiage and I'm going to translate it into English. So, it's on page 20 in the textbook. Here is on page 20 and it's theorem 1.3. And before I even forget to adjust the pen, do that. So, theorem 1.3. And I will write the fancy verbiage out. We're not actually going to sit and prove it, but I'm going to discuss what it actually means. So, we have assume A is an element of M of any matrix M of M by N. And then we have B is an element of M by L, not M by 1. And the augmented matrix that little dashed line means augmented matrix. Or it can be M by 1, it really doesn't matter. Well, for this theorem, I think it's 1. So, is the augmented matrix of a linear system? Okay. Then it says, suppose AB maps onto CD. And suppose you convert, and then it says suppose you convert A and B into CD. That's what that little symbol means or implies. You can also use it as converts. So it converts into CD, where of course C is element C is an element of M as an element of M. M by 1. And the augmented matrix is in row echelon form. Okay, it says the system is consistent if and only if D does not have a leading one. This is a lot of fancy verbiage, which we'll translate into English in a minute. Okay. Okay. If the system is consistent, you have two conditions. It has a unique solution. Where each column of C has a leading one, and for part 2, has infinitely many solutions, depending on Q parameters. Or C exactly has Q, so do not have a leading one. Okay, so it's a lot of fancy verbiage. Okay, let's translate that into practical English. Okay, what that means, it doesn't matter how many. Let me visualize the matrix for you. Let's visualize this. What we mean by leading ones is that it's going to be ones on the diagonal. So leading ones always occur on the diagonal. So once it's just like 1, 1, 1, dot, 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 dot. And so the 1, we'll call this 1 sub n, has a solution. Let's visualize what this means. Okay. Going back to the verbiage, going back to the fancy wording for a minute. Okay. The first is that each column of C has a leading one. So each column of C has a leading one. So that's what I need in this case here. Let's go to my new picture. So each column, this is our matrix C. Each column has a leading one. This column that column, so on and so forth, all the way down to the end. Okay? So each column has a leading 1. That's what it's saying. Okay? That's the first part. This is part 1 of the theorem. Okay? That's part 1. Each column has a leading 1. Okay? Then it says exactly cube infinitely many depending on q parameters where q is the number of zeros that do not have a leading 1. Okay? So this is the second situation that's going to be able to happen. Okay? In the second situation, we see this. You can have 1, 1, 1. And let's say, for example, this is going to be, this right here will stop at once at q. And this will be 0, this will be 0, 0, q, q. This will be q minus 1, actually. So, in the second situation, what we're saying is that the number of parameters will be 1 less than the number of zeros that you have. Okay? This is, again, matrix C. This is the column, this is the column. Alright, we have q parameters. What does that mean in practice? What does that mean in practice? Okay, q parameters means that I'm going to define parameters for everybody but the zeros I don't have. Okay? This is going to be part 2. Okay, q parameters. So for example, if I have 2 equations, I only need 1 parameter. If I have an infinitely many solution, why do I only need 1 parameter? Because the 1 row will have zeros in it, so it's 1 less than the total. Okay. If I have 3 equations, I need, well, obviously 2 parameters, because that's where I'm going to be covered. I'm going to have 2 variables I need to replace, so on and so forth. So if, in this case, if m the total number of variables q is equal to m minus 1. Okay? So the parameters that you define is dependent upon the number of equations. So number of variables in the equation or number of equations. Okay? I prefer the number of variables because the number of equations can be less or more depending on the situation, obviously. So in part 2 we speak of the need to define a parameter. So that's part 2 of the theorem and part 1 of the theorem. Okay? And then the extension of this particular point is steep. Okay, there's an extension of this theorem, which is called a corollary, or corollary. I learned corollary, so that's how I will say it for you. So, to translate the corollary, which is basically the same thing under the equation being 0. Okay. So it says, suppose, this is going to be, we'll call this C1. We'll call this C1. We'll call this C1.3. And so it says, suppose, and the fancy words. So suppose A is an element of a matrix M caution. M by N is the coefficient matrix of a homogeneous homogeneous means when there's zeros involved. Okay. Of a homogeneous linear system and C is row equivalent. A in row echelon form. What row equivalent means, of course, is that I use the elementary row operations to change A into C. Okay. Okay. And so, suppose that this is true. The system has the zero solution. If and only if. IFF means if and only if, by the way, because I'm lazy and don't feel like writing it out for you today. Okay. If and only if each call C has a leading one. Okay. Otherwise, the solution has infinitely many solutions. Regina Celi, Vicare, Alleluia, Resurrexit, Sicut dixit, Alleluia, ora pro nobis Deum, Alleluia. Laude, gaude, Gaude et letare Virgo Maria, Alleluia. Sicut quia surrexit Dominus veri, alleluia, oremus, Deus qui per resurrectionem Filii Tui Domini nostri Iesu Christi mundum letificare dignatus es, presta quesumus, ut per eus genitricem Virginem Mariam perpetue capiamus, gaudie vitae per aiuntem Christum Dominum nostrum. Oops, so we interrupted this lecture for the Regina Caeli because it's Easter, so the Angelus is not prayed. Instead, it is the Regina Caeli instead. Okay, back to the mathematics. So you see, otherwise, the solution has infinitely many solutions, and the number of parameters required number of columns not do not have a leading one in it. Okay. So the same kind of rule applies. So it's the same exact rule. Okay. Alright. And that's the two theorems that are in section 1.3. Basically, I wanted to cover them because I skipped them in the last video. And so now you should be able to survive the rest of the section. Okay. Oh wait, there's one more theorem. Yeah, let's put these theorems in really small proof, but it's the same theorem basically. It's talking about reduced row echelon form, which is the same thing. The only difference is everything is reduced to zeros in that situation. If you want more detail on how to do reduced row echelon form and row echelon form, you can check out the videos that I will post on those particular topics in particular. But since this is assumed to have been covered in linear algebra, this is assumed to be covered in precalculus and algebra 2, obviously there's no need to go into detail necessarily about that. Okay. So in the next section, we will talk about the algebra of matrices, how to add them, how to multiply them. Okay. How to add, how to multiply matrices, we'll talk about that in the next section. In a little bit of detail, not super detailed. Your book uses a bunch of notations, which I need to get familiar with. But the book uses it throughout, even though I personally don't use it. So that's the rest of the section, so we'll do 1.4 probably sometime maybe tomorrow.